We've all seen generative models nail observational data. You feed them a dataset, and they spit out synthetic samples that are statistically indistinguishable from the real thing. But here's the catch. Matching a joint distribution does not mean you've captured the causal structure. Two completely different causal mechanisms can produce the exact same observational statistics. And when you intervene, they break. This is the fundamental limitation of standard adversarial generative modeling. Today, we're diving into a rigorous new framework called Adversarial Causal Intervention Falsification, or ACIF. It reframes causal discovery as a minimax game where a structural generator doesn't just try to fool a discriminator with raw data. It has to survive a sequence of carefully chosen experiments designed to expose its flaws. We'll walk through the math, the theoretical guarantees, how it connects to active learning and generalized binary search, and how you can actually implement it with neural networks. If you work with causal inference, generative modeling, or experimental design, this is exactly the bridge you've been looking for. Let's start with the foundation. A structural causal model defines how variables are generated through structural equations and independent exogenous noise. Under causal sufficiency, these noise terms are mutually independent. When you intervene on a variable, by fixing it to a constant or shifting its mechanism, you change the data-generating process. The resulting distribution is fundamentally different from the observational one. The problem is that observational Markov equivalence means you can't distinguish between certain causal directions just by looking at passive data. You need interventions. But which ones? And how do you systematically test a generator against them? ACIF answers this by setting up a sequential game. On one side, you have a structural generator proposing a candidate model. On the other, an adversarial experimentalist selects an intervention from a feasible set. Between them sits an intervention-indexed critic. This isn't a standard real versus synthetic classifier. It's a two-sample test indexed by the intervention itself, checking whether the generator reproduces the correct post-intervention law. The generator only survives if it matches the true system across the interventions selected by its strongest adversary. Let's get into the formalism, because this is where ACIF shines. For each admissible intervention, we define a symmetric class of critic functions. The discrepancy between the true post-intervention distribution and the generator's prediction is measured by an integral probability metric. This is a broad family of distances that includes total variation, maximum mean discrepancy, and Wasserstein one distance, depending on your choice of critic class. The population objective of the game is the worst intervention discrepancy, penalized by the cost of the experiment. Mathematically, it's the supremum over all interventions of the IPM distance minus a cost term. The adversary's job is to pick the intervention that maximizes this penalized discrepancy. The generator's job is to minimize it. When the cost penalty is zero, the adversary greedily chases the largest post-intervention mismatch. When costs are positive, it balances falsification power against experimental expense. Here's the critical theoretical result. The zero set of this game is exactly the interventional equivalence class. If your generator achieves zero value, it means it's indistinguishable from the truth under every intervention in your query class. Point identification only happens when your intervention class is separating, meaning for any two distinct candidate models, there exists at least one intervention that exposes their difference. This clarifies a common misconception. You don't verify causality. You certify interventional equivalence over a tested family. True identification requires that the family actually separates your hypotheses. In practice, you don't have access to the true post-intervention distribution before running an experiment. So ACIF distinguishes between retrospective evaluation, where you reweight existing interventional data, and prospective selection, where you must choose the next experiment based on current uncertainty. The selector uses an ensemble or version space of surviving generators and picks the intervention that maximizes pairwise disagreement, again penalized by cost. Now here's where the theory gets beautiful. Under a condition called balance separation, this disagreement-driven selection rule eliminates hypotheses at a logarithmic rate. Balance separation means that at every step, there exists a feasible intervention that splits the remaining candidate models into two well-separated, roughly equal-sized groups. This is the causal falsification analog of generalized binary search. And when that condition holds, ACIF identifies the true model in its most logarithmic rounds relative to the size of the hypothesis class. If the hypothesis class is structured poorly, like a path-like family where each intervention only tests one edge at a time, this guarantee degrades to near linear, which perfectly aligns with classical active learning lower bounds. It's not magic, it's geometry meeting information theory. So how do you actually run this with neural networks? You replace the finite model class with a differentiable structural generator. You maintain an ensemble of models, or a variational posterior to represent uncertainty. The intervention policy is conditioned on this uncertainty state. The acquisition function becomes an expected disagreement metric. You generate samples under each candidate intervention for every model in the ensemble, compute pairwise IPM distances using your critic, and select the intervention that maximizes expected disagreement minus cost. After you run the intervention and collect real data, you update the ensemble by downweighting or removing models that exceed a confidence threshold under the new evidence. You also update the intervention-indexed critics, which are trained as standard two-sample discriminators, but conditioned on the specific intervention context. To prevent the selector and critic from colluding on easy distributional artifacts, you need practical safeguards. Balanced batches, critic regularization, cross-fitting, sample splitting, and a held-out set of interventions reserved strictly for final falsification. For the structural generator itself, you enforce modularity and acyclicity. Modular generators reuse unchanged causal mechanisms across interventions, which is what allows extrapolation. Acyclicity can be enforced with smooth penalties like the trace exponential constraint, keeping the optimization landscape tractable while respecting DAG constraints. Let's ground this in a concrete example. Consider two observationally equivalent linear Gaussian models, one where x causes y and one where y causes x. They share the exact same observational covariance. But under a hard intervention on x, their post-intervention distributions for y diverge completely. One shifts the mean proportionally to the causal coefficient, the other leaves it at 0. A Wasserstein 1 critic can detect this immediately. The adversary will choose the intervention strength that maximizes the signal-to-noise ratio, balancing the linear gain in discrepancy against quadratic cost. This closed-form solution matches numerical optimization exactly, proving the framework isn't just theoretical, it's computationally tight. In a more complex setting, take a 4-node path graph with 8 possible acyclic orientations. All share the same observational skeleton. When you run the disagreement-driven selection algorithm, it consistently identifies the true model in 1 or 2 rounds. Intervening on the middle nodes partitions the hypothesis space efficiently, achieving a split fraction that satisfies the balanced separation condition. A uniform random policy, by contrast, requires nearly 50% more experiments. The simulation doesn't just trend in the right direction, it matches the logarithmic bound exactly. That's the power of aligning experimental design with the geometry of the hypothesis class. I need to be clear about where ACIF doesn't work. If your admissible interventions don't separate your candidate models, you'll only identify an equivalence class. That's a mathematical limitation, not a training bug. If the true model isn't in your candidate class, ACIF returns a minimax approximation, the model with the smallest worst-case discrepancy. You can only interpret its value relative to your critic and intervention classes. Latent confounding breaks the independent noise assumption, so you'll need to extend to acyclic directed mixed graphs or explicit latent variable generators. And critically, the maximally discriminating intervention might be expensive, unsafe, or ethically impossible. The mathematical adversary is strictly subordinate to the experimental protocol. Feasibility, overlap constraints, and cost must be baked into the admissible set before optimization begins. ACIF reframes causal generative learning as repeated model criticism. The generator isn't rewarded for producing realistic observations. It has to survive the interventions on which plausible causal explanations disagree most. This shifts the discriminator from a generic quality judge to a family of causal falsification tests indexed by experimental actions. The correct mathematical endpoint isn't causality verified. It's that no admissible critic can distinguish this model from the system over the tested intervention family at the available resolution. If you're working on causal discovery, active experimental design, or robust generative modeling, this framework gives you a principled, theoretically grounded way to move beyond observational fitting. It connects adversarial training, integral probability metrics, and sequential hypothesis testing into a single coherent pipeline. I highly recommend diving into the full paper for the proofs, the implementation blueprints, and the ablation studies. Link it in the description. If you found this breakdown useful, subscribe for more deep dives into cutting-edge AI research. And let me know in the comments which part of the theory you'd want to see implemented next. Thanks for watching.